Hey guys, welcome to this session by Intellipaat. From playing a game of chess to driving cars and beating professional players in video games, reinforcement learning has recently become popular for doing all that stuff and much more. Now the self-driving cars actually drive on real roads with other cars, even carrying passengers, that too without any human assistance. In 2015, AlphaGo, an AI-powered system, defeated the world champion by 5-0 in a complex board game called Go. It was the first time that an AI conquered a human being in such a sophisticated game. So in this session, we are going to introduce you to the field of reinforcement learning. So now before we move on, do subscribe to our YouTube channel and press the bell icon so that you get a notification for our next video. So now let's look at the agenda for this session. So we'll start off by understanding what is machine learning and what are the different branches of machine learning. After that, we'll introduce you to the reinforcement learning and the learning process involved in reinforcement learning. Following which, we'll understand the elements of reinforcement learning and also we'll discuss the class of problems that we can solve using reinforcement learning. After that, we'll introduce you to the multi-armed bandit problems and we'll also discuss some methods to solve the exploitation dilemma. And at last, we'll discuss the Markov decision processes and we'll also see how to compute policies and value functions using beliman equations. Also, if you want to become a certified professional in reinforcement learning, Intellipaat offers a complete course on reinforcement training and certification. For further details, you can check out the description box below. So now, without any further ado, let's start with this session. So let's have a quick introduction or a brief introduction about machine learning. So you already know that a machine learning is the ability of a machine to learn by itself without being explicitly programmed. So we expose a machine to different experiences and based on the experience our machine learns from it, and this whole process happens without any explicit programming. And machine learning comes under artificial intelligence. Reinforcement learning also comes under artificial intelligence. So now let's discuss the broad classifications of machine learning. So machine learning can be broadly classified into three categories. The first category is called the supervised learning. The second category is called the unsupervised learning. And the third category is called the reinforcement learning, which is the main topic for this course. So now let's have a brief introduction about supervised learning. So in supervised learning, we train our machine on a labeled data. So we have both input and our labels, which is the correct input and output. So our machine knows and it learns from the right answers. So once it learns from the right answers, so then we supply our machine with new data and then it predicts new labels for us. So in supervised learning, we have two classifications, two categories. So for the first category is called the regression problems. So in regression problems, we predict continuous variables, which are also called numerical variables, using supervised learning. So we can predict, some of the examples are given here. So we can predict the stock prices or the product of different prices based on the previous data that we have supplied to our machine. And we can also predict population growth based on different factors that are related to population growth. Once we supplied our previous data to our machine, it will learn different patterns and correlations between different factors that are responsible for population growth. And in the future, it can predict for us at what point of time how much population growth will be there. And then we can also predict weather. So we can predict temperature or humidity or precipitation based on the previous data that we had supplied to our machine, and it learned different patterns and correlations from it. So these all categories, we are predicting a numerical output or a continuous variable. So that is why this is called a regression problem. And the second kind of problems that we can solve using the supervised learning are classification problems, where we classify or predict different categories. So we can, if we have 10 different images and if we want to know which image contains which object, so if you want to classify images based on the people or animals or any other object that is contained in them, so we can use the supervised machine learning. And then we have identity fraud detection. So based on our previous fraudulent cases or fraud records, when we supply those records to a machine, so it will learn patterns and correlations from those fraud cases, and in the future, if it finds any case that is suspicious and that is matching with the previous records or the previous patterns that our machine has observed, then it will tag that particular transaction as a fraudulent transaction. So this is very helpful in banking transactions to detect. So we can also use supervised machine learning in diagnostics to detect whether a patient has a disease or not, and what is the level of disease that patient has, so that in medical field also we can use supervised learning to classify whether a patient has a particular disease or not. So the next type of category of machine learning is called the unsupervised learning. So in unsupervised learning, we train the machine on unlabeled data. So in unsupervised learning, our goal is to identify the underlying structure in the data. So we have two types of unsupervised learning, broadly classified into two types. One is called the clustering, and then we have dimensionality reduction. So in clustering, we try to find different groups inside the data and the underlying structure of the data. So we can use for customer segmentation for different companies, and then targeted marketing, and then in our recommendation systems that are used by different websites like Netflix, YouTube. And then we have dimensionality reduction, which contains big data visualization. So we reduce the features, or we combine the features so that we can use different visualizations to visualize our data. Just a quick info, guys. If you want to become a certified professional in reinforcement learning, Intellipaat provides a complete course on reinforcement training and certification. For further details, you can check out the description box below. So now let's continue with the session. So we are not going to go too deep into these concepts because our main focus for this course is the reinforcement learning. So if you want to know more about these topics, then you can follow the machine learning course. So now let's move ahead and discuss the third type of learning, which is the main topic for this course, that is reinforcement learning. So reinforcement learning, which is also called the online learning, it is a type of machine learning where the machine learns from the environment. So instead of learning from a stored data, which is also called the training vectors, or machine learns from the whole environment. So the environment can be the real world, or it can be a simulated world. For example, in a video game, the world is a simulated world, and if you're trying to make a machine learning algorithm that plays a game, for that particular machine learning algorithm or reinforcement learning algorithm, the environment will be the particular game. So the reinforcement learning is based on the concept of rewards. So every time a machine does something, chooses the correct action, so we'll give it a positive reward, and the reward is always a real number. So if a machine does the action which is appropriate, so we'll give a positive reward, and if it is not appropriate, we'll give a negative reward, which is also called the penalty. So the goal of our machine learning or the reinforcement learning algorithm is that it has to maximize the number of rewards, and the maximization is not only short term, but it has to maximize the long term rewards. So the goal of a reinforcement learning algorithm is to maximize the scalar rewards, and the rewards are always a real number. So we also say that reinforcement learning is a memoized search. So our algorithm will search for the right ways to do something, and it remembers that way. So instead of just telling what goal we want to achieve, we just tell our machine learning algorithm or reinforcement learning algorithm to maximize the scalar rewards. So now let's look at the process that is involved in our reinforcement learning. So the main idea behind reinforcement learning is that we have an agent who is trying to maximize the scalar rewards, and it learns from the environment, and the reward is given by the environment to the agent. So let's take an example where we have a footballer who is trying to score a goal. If the footballer is not able to score a goal and the goalkeeper catches the ball, so we'll give a reward of -1. So it will be a negative reward. So once our footballer gets a negative reward, it knows that it doesn't have to perform the same action again. So it will try to avoid the action that gives it a negative reward. So next time, if the footballer is able to score a goal, so we'll give a reward of +1. So in reinforcement learning, or agent, once it knows that this action leads to the appropriate action, so it yields a good reward. So it will not only perform that action but also remember the action. So that is why it is also called a memoized search. So now let's discuss some of the main elements or some of the terms that are involved in reinforcement learning. So there are main basic 7 terms. So there are a lot of other terms that will be introduced to you in the further modules. So then agent, which is the first term that I have already used before. So an agent is just something that we are trying to put intelligence into. So our agent can be a robot, or it can be an algorithm that plays a game. So the agent in RL is a component that makes decision of what action to take. So we also call the agent as a decision maker. And then we have something called environment. So environment is the setting on which the agent is performing the action. So the environment is everything that the agent is working on. So environment can be a real world. So if we have a robot and he's learning how to work, so its environment will be the whole world of the path that he's trying to walk on. And then environment can be a simulated world, so it will be a game. So if our agent is trying to learn how to play a game, so that environment will be the game environment for that particular agent. And then we have a state. So in a state, we define what are the different characteristics and what is the current situation of an agent. So if an agent, for example, if you take the example of our footballer, and when a footballer scores a goal, so that will be a particular state where it got a reward, and the other state will be when it doesn't score a goal. So that will be another state. And if you take the example of a robot, if the robot is trying to walk, so it will take the right step. So once it takes the right step and it is still stable, so we say that is another state. And if it takes another step and it destabilizes itself and it falls down, so that will be another state. And then we have action. So if you take the football example, so the action will be kicking the football. So if and the direction in which the footballer will kick the football and the speed that it will take to click the football, so that will be a particular action. So the action are the agent's methods which allow it to interact with its environment and thus transfer between states. So after taking an action, an agent will transfer from one state to another. So if you have a robot who's trying to learn to walk, so once it takes an action, that is the action will be put the right leg in front of it, so that will be an action. And once the action is done, so that robot will be in new position, so that position will be a new state. So the transition between different states happens because of actions. Just a quick info, guys. If you want to become a certified professional in reinforcement learning, Intellipaat provides a complete course on reinforcement training and certification. For further details, you can check out the description box below. So now let's continue with the session. So when a robot or when an agent takes an action, it will either yield a negative reward or it will either yield a positive reward. And the job of the environment is to give the positive or negative reward. And based on our goal that we are trying to maximize, we'll either get a positive reward and negative reward based on the actions that an agent takes from one state to another. And then we have something called policy. So it is policy is a mapping from one state to another. So if you are in one state, so if you take the example of a robot which is still standing, so there are different actions that robot can take. So a policy will define which action is the best one and what action should the robot take so that it receives the best reward. So it is just a mapping. A policy is a mapping from a state to an action. And then we have something called value function. So we use value functions to define policy. So value functions actually determine which is the best action in a particular state. So we have multiple actions in a particular state, and each action has a particular value function, and each state also has a particular value function. And based on those value functions, we define a policy that our agent will use to select an action or transition between different states. And it is noted by V of S. We'll learn more about these concepts in the coming modules. So now let's see what are the different type of RL agents that we can use and we can train. So now let's discuss some of the types of RL agents that we can will use in this course. So there are two types of RL agents. One are the model-based agents, which keep an explicit model of the environment. So a model is just a representation of how the environment changes when an agent performs an action or transitions from one state to another. So if an RL agent keeps the model or the representation of the whole environment and how it changes when it takes an action, so that those models will be, or those agents will be model-based agents, and they have to compute value functions and policies at every single time. And they may not have values or policies function also. So we'll discuss this later on in detail. So the next type of RL agents can be model-free RL agents. So these agents, they do not keep any representation of how the environment changes when they take an action or they transition from one state to another. So they calculate value functions and policy functions to take decisions and to move from one state to another and to choose which action to take from moving from one state to another. Now let's discuss some of the problems that we can solve using the reinforcement learning methods. So the first type of problems that we are going to solve in this course are called the multi-armed bandit problems. So these problems also require the sequential decision making. So we are teaching our agents how to make decisions in a sequence. And the first type of problems that we are going to discuss are the multi-armed bandit problems. So we'll discuss this in detail in the next module. Also in the next module, we'll also discuss the Markov decision processes, which are also used for making decisions under uncertainty, and how we'll see how Markov decision processes are different from multi-armed bandit problems, and what are the similarities and what are the dissimilarities, and what are the different techniques that we can use to solve these problems. So let's start with the first class of problems that we can solve using the reinforcement learning, called the multi-armed bandit problem. So the multi-armed bandit problem or the K-armed bandit problems are used to formalize or define the problem of decision making under uncertainty. So the idea behind the multi-armed bandit is that you have a slot machine, which is also called a bandit because its sole purpose is to loot your money. So a multi-armed bandit has multiple levers, or if we have multiple bandits with a single lever, then also we say that we have multi-armed bandits. And how it works is that you put a coin inside the machine and then pull a lever attached to it, and if you are lucky enough you will get a reward, or otherwise you will not get a reward and end up losing your money. So in this scenario, you are an agent and you have to choose between k different actions, which in this case are k different levers of these bandits, and then receive a reward based on the action. And we also believe that there is a probability distribution for the reward corresponding to each lever, which actually means that there will be at least one lever which gives us more reward, and the reward distribution for every lever is different and is unknown to us or the gambler who is playing the game. So this is why we say that it is a problem of decision making under uncertainty. So our goal here is to identify which lever to pull in order to get the maximum reward after a given set of trials. Just a quick info, guys. If you want to become a certified professional in reinforcement learning, Intellipaat provides a complete course on reinforcement training and certification. For further details, you can check out the description box below. So now let's continue with the session. So now let's see some use cases where the multi-armed bandit problems are used. So our first use case will be clinical trials. So suppose you are a doctor and you want to test 3 different medicines on your patients in order to know which medicine works the best. So you give the first medicine to a patient and the patient turns out to be satisfied with it. And then you give the second medicine to the next patient and he turns out to be unsatisfied with it. So you would keep on doing this until you have enough information about the effectiveness of the medicines. So this problem constitutes as a bandit problem since we have 3 different medicines to choose from and we are uncertain about the effectiveness of these medicines. And our next use case is the online advertising. So suppose you have 3 different versions of the same ad and you want to know which ad has the highest click-through rate. So you start by displaying the first ad to the first customer or first ad to on your website, and the first person who logs onto your website clicks on the ad, and then you display the second ad on your website and the next person who logs onto your website does not click on the ad, and then you display the third ad on your website and the person who logs onto your website does not click on the ad. So you would keep on doing this until you have enough information about the ad having the highest click-through rate. So this problem also constitutes as a multi-armed bandit problem since we have 3 different versions of a same ad and to choose from, and we are uncertain about the click-through rates of these ads. So now let's discuss a very important concept in reinforcement learning called the action values. So in our online advertisement example, if you already knew which ad has the highest click-through rate, so it would be very easier for us to choose which ad to display. But that does not happen in real life. So we will run many trials until we have enough information about the click-through rates. But one thing we can do is we can use all the previous collected data to know which ad is best so far. So we'll quantify the value of taking each action, which in our case in our example is choosing which ad to display using the action values. So the value of selecting an action Q star is the expected reward received after that action is taken. So the goal of an agent is to maximize the expected reward, and that can be achieved by selecting the action among all the actions that an agent can take that has the highest value. So the value of Q star, which is the expected reward received after an action has been taken, is actually unknown to us beforehand. So we would have to find a way to estimate the value of Q star so that we can choose the best action, which in our doctor example is the best medicine. So we'll use a method called the sample average method to estimate the action value for a particular action. So the action value for an action A at time t is the sum of the rewards received when action A was taken before time t divided by the total number of times action A has been taken before time t. So in our doctor example, if the patient is satisfied with the medicine, then we will give a reward of +1, and if the patient is not satisfied with the medicine prescribed by the doctor, we'll give a reward of 0. So now let's see how action values are calculated using the sample average method in our clinical trials example. So the doctor prescribes the first medicine to a patient and the patient turns out to be satisfied with the medicine, and hence we'll give a reward of +1 to this action. So the action value for this action is 1 since the total reward received till now is 1 and the action has only been taken once. And similarly, the action values for the second and the third action are 0 since we have not taken this action before this particular action. So now another patient comes in and the doctor prescribes the first medicine to the patient and the patient turns out to be unsatisfied with it, and hence will give a reward of 0. And the third patient comes in and this time the doctor chooses the second action, which is the second medicine, and the patient turns out to be satisfied with the medicine. And then the fourth patient comes in and this time the doctor chooses the third medicine and the patient turns out to be unsatisfied with the medicine, so we'll give a reward of 0 to this particular action. So now now if we calculate the action values up to this point, we'll get the following action values. And suppose we keep on doing different trials for the medicines, and then at the 12th trial we end up with the following action values. So as you can see, the more trials we perform, the closer our action values estimate gets to the actual action values. So now we have the action value estimates for each action, and now if the doctor wants to choose which medicine to prescribe to the next patient, so we have two options. Either he can choose the medicine having the highest action value, which is called a greedy action, where he exploits the current knowledge he has about the action values, or he can choose the other two medicines so that he can find a more accurate estimate for the action values, which is also called selecting the non-greedy action or exploring in order to get closer to the actual action values. So now we have come down to the process of selecting the actions. So the greedy action is when we choose the current highest estimated value, which means that we are exploiting the current knowledge that we have. Or we can choose to explore further by selecting the non-greedy action, hoping that we'll get more information about the other actions. But an agent can only select one action at a time, either the greedy or the non-greedy. So that brings us to this challenge that we face in reinforcement learning called the exploration versus exploitation dilemma. So the exploration allows an agent to improve its knowledge about each action in order to gain a long-term benefit. And on the other hand, the exploitation allows the agent to choose the greedy action and try to get the most reward, this time that may be for a short-term benefit. And one issue with exploitation is that it can lead to a suboptimal behavior. So let's discuss how it can lead to a suboptimal behavior with an example. So in our clinical trials example, if we choose to exploit after the first trial, which is the Q1, so we'd keep on choosing the first action because it has the highest estimated value. But we know that after 12 trials, our second action, as we explore more, we find that the highest reward is actually returned by the second action. So that is how, if we do not choose the right point of exploitation, we can fall into this trap where we choose a suboptimal action instead of choosing the optimal action. So now how do we actually know when to explore and when to exploit so that we do not end up choosing a suboptimal action? So now in order to learn how to balance exploration and exploitation, let's discuss our first method, which is called the Epsilon-Greedy. So Epsilon-Greedy is a simple method to choose between exploration and exploitation. So in Epsilon-Greedy, the epsilon, which is typically a small number, it refers to the probability of choosing when to explore. So in Epsilon-Greedy, we mostly behave greedily by selecting the greedy actions. But once in a while, we'll choose an action randomly among all the actions with an equal probability of epsilon without considering the current action value estimates. So this is how we actually choose an action in Epsilon-Greedy. So a random action is chosen with the probability epsilon, and for the rest of the time we choose to exploit the current highest value estimate. Here the argument max A simply means that we need the action, or we want to find the action that maximizes the current value estimates, which is given by Q of A. So by doing that, we sample every action among all the actions an infinite number of times, and we ensure that all the action value estimates, they converge to the actual action values of those actions. So we choose to explore epsilon percentage of the times, and we exploit 1 minus epsilon percentage of the times. And the typical values that we use for epsilon and or for exploring are 0.01, which is 1%, 0.05, that is 5%, and 0.1, that is 1%. So this is a pseudocode that we'll use for Epsilon-Greedy. So here we take P as a random number between 0 and 1, and if the value of P turns out to be less than the value of epsilon that we have chosen, we'll select a random action, which is also called exploration, and otherwise we'll choose to exploit by choosing the current best action. So now let's go to the Jupyter notebook and implement Epsilon-Greedy algorithm in Python. So we'll start by importing the required packages, that is NumPy and Matplotlib. So NumPy we'll use for creating arrays and functions related to arrays, and then we'll use Matplotlib for plotting or values. And after that, we have defined a class called actions, which will be used to define the attributes and the methods related to our actions. So the constructor of the class takes one parameter, that is m, which is the actual value or the actual action value for our action, and we have defined two instance variables, that is mean and n, where mean will be our estimated action value and n will be the number of times we want our Epsilon-Greedy algorithm to run. Next, we have defined a function called choose, which will randomly choose an action from the actions that will pass to our class. And then we have also defined an update function which will update the value of the estimates after we choose an action X. Then we have defined a run experiment function which takes different values of M1, M2 and M3, which are the actual values for 3 actions. And we also pass a value of epsilon as EPS, and NA stands for the number of times that we want our Epsilon-Greedy algorithm to run. So we want our run experiment function to return the cumulative average as a list named data. So a list named data will contain the estimated values for our actions after the n runs are completed. So here you can see that we have defined our Epsilon-Greedy algorithm inside this for loop, where we have taken P as a random number between 0 and 1, and the value of P, if it turns out to be less than the epsilon that will pass to this function, then it will randomly choose an action among the 3 actions, and otherwise it will choose the action with the best current value or the current value estimate. After that, we'll plot our cumulative averages that we have defined above, and we'll compare it with the actual values which our actions have to see how our Epsilon-Greedy works on different values for the actions. And we'll plot this in log scale as well, so that we can see the fluctuations in the earlier rounds clearly, since the later data is squished in a log scale. And in the last, we have printed the value of the estimates that our Epsilon-Greedy will calculate. So after that, we'll run our experiment. Just a quick info, guys. If you want to become a certified professional in reinforcement learning, Intellipaat provides a complete course on reinforcement training and certification. For further details, you can check out the description box below. So now let's continue with the session. With 3 different means, which are the actual values for our actions. So the first section has a mean of 1, second action has a mean of 2, and the third action has a mean of 3. So among these 3 means, our action 3 has the highest mean. So our Epsilon-Greedy should converge to this mean because this action has the highest return or reward. So here we have chosen an epsilon of 0.1, which means 10%. So our Epsilon-Greedy algorithm will explore 10% of the times, and 90% of the times it will exploit. And we'll run the Epsilon-Greedy algorithm 100,000 times. So this is the plot that we get after running our Epsilon-Greedy algorithm 10% of the 100,000 times with epsilon as 10%. So these are the estimated values for each action that our Epsilon-Greedy value or Epsilon-Greedy algorithm has calculated. So the actual value was 1 and it has calculated this value, and the actual value was 2 for our second action, and our Epsilon-Greedy algorithm has calculated this value. And the actual values for action 3, which our Epsilon-Greedy has calculated this particular value. And this is the graph which our Epsilon-Greedy uses for different iterations. And in the last iterations, when it reaches 100,000 iterations, it normally almost converges with our best mean or the best action that we will have defined. And now we'll run this experiment with the same 3 means 1, 2 and 3, and now we'll choose an epsilon of 5%, that is 0.05. And this is the plot that we'll get, and these are the estimated values for 3 different actions that our Epsilon-Greedy algorithm will calculate. And now if we run this experiment with epsilon as 0.01, which is 1%, so here you can see these are the estimated values that our Epsilon-Greedy algorithm has calculated, and this we have run this for around 100,000 times. So now we'll compare these 3 epsilons in a single plot. So we'll firstly plot a log scale plot. So in a log scale plot, our initial values are expanded and the last values are converged or they are squished. So here you can see the green line represents the epsilon value of 0.01, which is the 1%. So this Epsilon-Greedy algorithm will explore 1% of the times. And then we have epsilon equals 1 or epsilon equals 0.1, which is 10% of the times. So our blue line will explore 10% of the times, and our orange line will explore 5% of the times. So in the beginning rounds, you can see the algorithm that is performing the best, which is our orange line, that is 5%. But later on, when the runs become huge, so you can see the green line, it is closer to the best value estimate, that is 3. And now if you compare different epsilon values using a linear plot, which won't show you the actual fluctuations in the beginning. So our log scale plot will show us the actual fluctuations between different values of the epsilons that we have taken. So now that we have discussed the Epsilon-Greedy algorithm, and before knowing the limitations of Epsilon-Greedy and moving to the next algorithm, let's first discuss an important concept that we'll use throughout the course. So now we know how to calculate action values using the sample average method, but now we'll turn to the question of how these averages can be computed in a computationally efficient manner. So the obvious implementation is to maintain a record of all the rewards that we have received and then perform this computation where we estimate the new value whenever we need the new estimated value. However, if this is done, then the memory and the computation requirements would grow over time as more rewards are received. So each additional reward will require additional memory to store it and then an additional computation to compute the sum of this particular numerator. So to overcome this problem, we'll write the sample average method in a recursive manner, and by doing so we can avoid storing all the previous data. So this is the equation that says the same thing, that will sum all the rewards divided by total the number of times we have taken that action. So we'll overcome this problem by writing our sample average method in a recursive manner, and to do so we are going to take out the current reward out of this summation, which is Rn. So now the sum only goes until the previous reward, and now we'll write our next value, which is Qn plus 1, in terms of our previous value estimate, that is Rn minus 1. And so to do so, we'll multiply our summation term with, we'll multiply and divide the summation term with n minus 1, and by doing so we are just actually multiplying by 1 because these two terms will cancel out, n minus 1. So now if we look closely at the summation term, this is just the definition of our Qn, which is the current value estimate. So we can simplify this equation a little further. So we'll distribute Qn to get this form, and finally we'll pull out the nQn term from here and multiply by 1 by n. So we'll get this equation. So now we'll have an increment update rule for estimating values where alpha is a function of n, and which is typically a number between 0 and 1. So we can write this equation in this form. So in this equation, the error in the estimate is the difference between the old estimate and the new target, and to reduce the error we will take a step towards the new target, and that will create a new estimate. And here the target value is the new reward, and the size of this step will be determined by your step size parameter and the error in the old estimate. So now we have an equation that we can use to update the action values incrementally without storing the previous values. So let's say if the value of alpha is set to 0.1, which is very small number, then the most recent rewards, which is Qn, will have more effect on our new estimate. And if the alpha value is more, that is say 0.9, then our new estimate will have more weight of the previous rewards as well. So this concept is actually used when our reward distribution changes with time. So the value of the rewards by taking the same action changes with time, and which we also call as a non-stationary bandit problem. So we'll use this rule throughout the course to solve our non-stationary bandit problems. So as we have already discussed the Epsilon-Greedy and the incremental update rule. So in Epsilon-Greedy, one problem is that we'll eventually get to a point where we are still exploring when we actually don't need to explore anymore, since we would have already found the best action value estimate. So now we'll move ahead and discuss the next method for balancing exploration and exploitation, called the optimistic initial values. So in optimistic initial values method, we balance the exploration and exploitation by being optimistic in the face of uncertainty. So instead of defining the initial values as 0, we'll define a non-zero initial estimate to encourage early exploration. So the first time any action is taken, the observed reward will be smaller than the initial estimate which is set by us, and by doing so, the estimated value for the chosen action will decrease compared to the other actions, and hence all the other actions will be explored more. So now let's discuss this concept with the help of an example. So we'll take an example of online advertising. So we have 3 different versions of the same ad, and we want to know which ad would have the highest click-through rate. So instead of initializing the action values estimates to 0, we'll behave optimistically by making the initial values for each action as 2, and to make sure we are definitely overestimating, we have set the values as 2. And let's assume that we always choose the greedy action, that is the action that has the highest estimated value. So we'll use the incremental update rule, and we'll take the alpha as 0.5 for this demonstration. So the first person logs onto the website, and because the values of actions are equal right now, so we'll choose an ad randomly. So we choose the first ad to display, and the person clicks on the ad, and we'll give a reward of 1. And now if you calculate the estimated values, you can notice that the estimated value for the first ad will decrease from 2 to 1.5, even though the ad was a success. And this is because the reward was 1, which is actually less than our initial optimistic estimate of the value. So now the next person logs on to the website, and so we can choose amongst the ads which has the highest estimated value. So we have add 2 and add 3. So we'll choose the second ad to display, and the person does not click on the ad. So we'll give a reward of 0, and then it will lower the estimated value for the ad. So now the estimated value has decreased to 1, which is actually lower than the estimated value for the first ad. So now let's say the third person logs onto the website, and since the ad 3 has the highest estimated value, so we'll choose ad 3 to display, and the person clicks on the ad. So we'll give a reward of 1, and now if you calculate the estimated values, the estimated values will decrease to 1.5. So therefore people will keep logging onto the website and will continually display the ads and refine the value estimates. So from this example we can see that using optimistic initial values encourages exploration early in the learning, and we have tried all the 3 ads in the first 3 steps you can see here, and we'll continue to try all the 3 ads afterwards. So now let's go to the Jupyter notebook and implement optimistic initial values, and compare it with Epsilon-Greedy to see which method performs better. So this is our first algorithm, that is Epsilon-Greedy, that we had implemented before. This is our Epsilon-Greedy. So we will just have to change this code. So now let's go to our optimistic initial values, how we define that function. And now we have set the run experiment function for our Epsilon-Greedy as run experiment EPS. So we'll define our optimistic initial values function. So here in this class, which is our actions class for optimistic initial values, instead of keeping the mean, which was 0 before, we'll keep an upper limit which we'll define as a number which is highly overestimating, or our initial value estimate that we'll keep for our actions. So instead of 0, which was in EPS, we'll keep an upper limit, and then we'll define a function called run experiment, which is for our optimistic initial values, and here we have defined the upper limit as 10. So our initial value for the action value estimates will be 10, and then we have our 3 actions M1, M2 and M3, which will contain the actual values for these actions, and n is the number of times that we want to run our algorithm for. So we'll define our optimistic initial values function here, which is just to choose the best action or the best estimated value in all the actions. So if we plot our EPS, which is our Epsilon-Greedy algorithm, so these are the 3 action values for our 3 actions, and we have chosen an epsilon of 10%, that is 0.1, and we are running this algorithm for 100,000 times. So we'll get this type of plot here, and these are the estimated values which are calculated by our Epsilon-Greedy algorithm. So now if we run our optimistic initial values function with 3 actual means, and since our upper limit is 10, so it means our action values will start from 10. Optimistic initial values will be 10, and we'll run this for same 100,000 times. So here you can notice in optimistic initial values, since we have explored in the beginning, so in the beginning you will see that our algorithm explodes a lot. In the later runs it converges to the best action value, that is 3, and these are the estimated values by our optimistic initial values algorithm. And now if we compare both of these algorithms to see which performs better, so we'll compare it using the log scale first, which will show us this kind of plot. So here you can see the orange line is our optimistic initial values, and the blue line is our EPS algorithm. So here you can clearly see that in the beginning or orange line it explores a lot, but in the later runs of the algorithm we can see that it performs better than our EPS, which is 1%, which would explore 1% of the times, and our optimistic initial values is the blue, is the orange line. And you can compare it using the linear plot as well. So in the linear plot also you can see that our EPS, which is the 1% exploring EPS, and our optimistic initial values, so the orange line, which is for the optimistic initial values, it performs better than our EPS algorithm. So as we have already discussed the optimistic initial values method, but one limitation of optimistic initial values method is that it drives exploration only in the early rounds, and this means that the agent will not continue to explore after some time, and this leads to issues in the non-stationary problems where the value of one action may change after some number of time steps. So an optimistic agent will not notice that a different action is actually better now. And another limitation is that we may not always know how to set the optimistic initial values, because in real life scenarios we may not know the actual reward or the maximum reward that we can get from an experiment. But we often use the optimistic initial values approach in combination with other exploration approaches. So now let's move on and discuss the third approach for balancing exploration and exploitation, which is called the upper confidence bound action selection. So the upper confidence bound action selection actually uses the uncertainty in the estimates to derive exploration. So since we are estimating our action values from a sampled set of rewards and not the whole population of the rewards, so there is always an inherent uncertainty in the accuracy of our estimates. So it would be better to select actions among the non-greedy actions for exploration according to their potential. So if their potential is actually being optimal, so which can be done by taking into account both how close their estimates are to the maximum and how uncertain those estimates are. So we use upper confidence bound to select actions using the uncertainties in those values. So this is the formula that we use to calculate the upper confidence bound for a particular action. So we'll select the action that has the highest estimated value plus our upper confidence bound exploration term. So here T is the number of steps that we have taken so far, and N is the number of times that we have taken the action A. The C parameter here is a user specified parameter that actually controls the amount of exploration. So we can clearly see how UCB actually combines both exploration and exploitation. So the first term here is called the exploit term. So this represents the exploitation part, and the second term represents the exploration part. So let's discuss this with the help of an example. So here Q of 1 represents our current estimated value for action 1, and the box is a confidence interval around Q star of 1, which says that we are confident that the actual value of action 1 lies somewhere in this region. So the upper line is called the upper bound and the lower line is called the lower bound, and the region in between is called the confidence interval, which represents our uncertainty. So if the region is very small, we are very certain that the actual value of action 1 is near our estimated value, and if the region is very large, so it means we are uncertain that the value of action 1 is near our estimated value, that is Q of 1. So in upper confidence bound, we say that if we are uncertain about something, so we should optimistically assume that it is the best choice. For example, we say we have these 4 actions here and we have the associated uncertainties with our actions. So our agent right now has no idea which is the best action. So in UCB, it will automatically or it will optimistically pick the action that has the highest upper bound, so which is Q of 1 here. So by taking this action, either we'll get a good reward or we'll get a reward, or by taking, if we don't get a reward, we'll get to learn about this action that we know least about, because confidence or the uncertainty in this particular action is large. So we'll get to know about this action if we don't get a reward. So let's say we take that action and we don't get any reward. So the value of Q of 1 will now decrease since we have added another example to our sample, and also our confidence interval will shrink since we have added another example to our sample. Now our UCB will select the action that has the highest upper bound. So right now the action that has the highest upper bound is Q of 2, and let's say that we get a reward after selecting this action. So now our estimated value will increase, and since we have added another example to our sample, so our confidence interval also shrinks. So the more number of examples we add to our confidence intervals, it shrinks because we then get closer to our actual values. So again, since Q of 2 has the highest upper bound, so it will be selected again. And let's say this time we don't get any reward after selecting Q2 for repeatedly for n number of times. So which means that the estimated value will decrease and the confidence interval also shrinks. So now our algorithm will select the action which has the highest upper confidence bound, that is action 3. And suppose we get a reward, so the estimated value of this action will increase and also the confidence bound will decrease or it will shrink. So now we'll keep on doing this until we eventually get to an action that has the highest action value. So this is how the UCB algorithm converges to the best value, and it will select the action that has the best value based on the confidence bounds and the uncertainties in the estimates. So now let's compare the upper confidence bound and the Epsilon-Greedy algorithm and see which algorithm performs better. So this is the plot actually that we get after plotting the UCB and the Epsilon-Greedy, and here you can clearly see that our UCB algorithm, which is represented by the orange line, it performs better than our EPS, which is our Epsilon-Greedy with 10% exploration rate. And since in the beginning rounds only we can see that the UCB algorithm performs better because it will choose the optimal action, and the optimal action is chosen on basis of both the higher estimates and the uncertainties in those estimates. And later on also you can see in later rounds our UCB is still performing better than our Epsilon-Greedy. So after learning about the multi-armed bandit problems, which introduce many interesting questions, however, they do not include many aspects of the real-world problems, such as when the agent is presented with the same situation and each time it will choose the same action. So in many real-life problems, different situations call for different actions. So these actions we choose right now will affect the amount of reward we can get into the future. So that brings us to our next set of problems that we can solve using the reinforcement learning methods called the Markov decision processes. So MDPs, or the Markov decision processes, are used to define the problem of sequential decision making where the current actions are not only influenced by the immediate rewards but also the future situations or states. So the bandit problem, they do not take into account for the fact that different situations may require different actions. But in MDPs, we balance the trade-off between the immediate reward and the delayed rewards. And the future state and reward will only depend on the current state and the action. So it does not depend on the previous action and the time of the action. The future state and the reward, it will only depend on the current state and action, which is also called as the Markov property. So let's discuss this with the help of an example. So let's take a robot as our agent and whose goal is to solve this maze, and also by collecting the objects along the way. So each object has a specific reward associated with it. So if a robot collects a rugby, it gets a reward of +10, and if it collects a flag, it gets a reward of +5. So now if you follow the approach of a multi-armed bandit problem, we'll choose the action that generates the maximum reward. So that is, the robot will choose to go left, but now the robot, this is left from our side, so that is right from the robot's side. So now when the robot will choose to go for the rugby, but now the robot is in a different situation where it cannot go further since there is a wall in front of it, and when it hits the wall, it will get a reward of -100. So but now if you follow the framework of a Markov decision process or MDP, the robot will choose to go and collect the flag instead of the rugby, because it knows that after collecting the flag, it will be able to solve the maze, and by solving the maze, it gets a reward of +100. So this is one such situation where accounting for delayed rewards maximizes our total reward. So we can formalize this interaction with a general framework. So in this framework, the agent and environment, they interact at different time steps. So at each time t, the agent will receive a state s of t from the environment, and it is from the set of all the possible states, that is script s. So based on this state, the agent will select an action, that is a of t, from the possible set of actions that we have, which is a of s. For example, if our agent selects to move left to collect the rugby ball, so that will be our action a of t at time 0 or time 1. So one step later in the part of the agent's action, the agent will find itself in a new state, that is st plus 1. For example, if the state where the action is taken and the robot is in a new state where the robot is next to the wall after it collects the rugby ball, and the environment, it will also generate a scalar reward, that is rt plus 1, which will be drawn from the set of possible rewards, that is script r. So in this case, the reward is +10 for collecting the rugby ball. So this diagram actually summarizes the agent environment interaction in an MDP framework. So the agent environment interaction generates a trajectory of experiences. So this is a trajectory of experiences consisting of the states, actions, and the rewards. So states will be S0, A0, and the reward will be generated when the state transitions from one state to another. So the actions influence immediate rewards as well as the future states, and through those future states, the future rewards. So as in multi-armed bandit problems, the outcomes in an MDP are stochastic, so which means that when the agent takes an action in a state, there are many possible actions, or there are many possible next states and rewards. And therefore, we use the language of probabilities to define the dynamics of an MDP, and we do it by defining a probabilities distribution. So here the transition dynamics function P defines this notion. So in a finite MDP, given a state S and action A, P tells us the joint probability of the next state, that is S prime, and a reward R. So since P is a probability distribution, which is called the dynamics function or the dynamics of the MDP, so it must be non-negative, and its sum over all the possible next states and rewards must be equal to 1. And also note that the future state and the reward, they only depend on the current state and the action, which is called the Markov property. So which actually means that the present state is sufficient enough, and remembering the earlier states would not improve the predictions about the future. So now let's discuss MDP with the help of an example. So let's consider a recycling robot which collects empty cans in an office environment. So it can detect the cans and pick them up and drop them off in a recycle bin. So the robot actually runs on a rechargeable battery and its goal is to collect as many cans as possible. So we'll start with the states, actions and rewards. So let's assume that the sensors can only differentiate between two charge levels, that is low and high. So these charge levels actually represents the robot's state. So in each state, the robot has three choices. So it can either search for the cans for a fixed amount of time, or it can remain stationary and wait, or it can go to the charging station and recharge its battery. So we allow only recharging from the low state because recharging is pointless when the energy level is already high. So now let's draw the transition graph for this particular MDP. So first let's try the states using the circles high and low, and searching the cans when the energy level is high might reduce the energy level to low. So that is the search action that we can take from the high state. So that's the let's say that the search action in the high state, it does not change the battery level, so the state won't change. So let's say the probability is alpha when and the search action in the state high might not change the state, or the energy level might drop to the low with the probability of 1 minus alpha. So in both these cases, the robot's search returns the reward of our search. So the robot can also wait, and waiting for the cans and does not change the battery, does not drain the battery, so the state does not change. And in both the cases, we'll have the wait action and it will return a reward of our wait. And searching for the cans when the energy level is low might deplete the battery completely, and then the robot would have to be rescued and recharged again. So let's write the probability as 1 minus beta, and if the robot is rescued, then its battery level is restored. However, needing rescue returns a negative reward of R rescued, which we have mentioned as -3 because the robot has messed up. So alternatively, the battery might not run out, and this occurs when with the probability beta and the robot receives a reward of R search. Or alternatively, it can also recharge, and the recharge action actually restores the battery to the level high and the robot receives a reward of 0. So that is how we can formulate or draw a transition graph for any MDP. So this is the table that we can use for state transitions. So here you can see the state are high and low, and with the state we have mentioned each action and then the next state. So if the state is high and we search, the action is searched, so we'll be in state high or we'll be in state low. So the probability of being in state high is alpha and the probability of being in state low is 1 minus alpha, and will return a reward of R search. And similarly for some states, you can see the states do not exist, because if you are in high state and if we wait, so it is not possible to go to low state, so the probability will be 0. And when we are low state and we wait, so it is obvious that we'll stay in the low state, so the probability will be 1. So this is the table that mentions states, transitions, and along with the probabilities and the rewards. So in reinforcement learning, the agent's goal is to maximize the future reward, so which is defined by the reward hypothesis, so which actually states that all of what we mean by goals and purposes can be well thought of as a maximization of the expected value for the cumulative sum of received rewards. So which actually means that in reinforcement learning, the purpose or the goal of the agent is to maximize the cumulative reward it receives in the long run. So which means that we not only maximize the immediate rewards but also maximize the total future reward. So now let's understand this definition thoroughly. So we say that the return at time step t, which is denoted by gt, is the sum of rewards obtained after time step t. So the return gt here is a random variable because the dynamics of the MDP can be stochastic. So which means that there is a randomness in both the individual rewards and the state transitions. So in general, we can say that there can be many different trajectories from the same state. So which sometimes we might get a large return, and sometimes we might get a smaller return from the same state because there is a randomness in our MDP. So that is why we maximize, instead of maximizing this return, we maximize the expected return. So which is denoted by this term here, which is called the expected return. And then for this approach to be well defined, the sum of the rewards must be finite. So specifically, we can say that there is a final time step t where the agent and the environment interaction ends. So in the simplest case, the interaction should naturally break into different chunks, which we also call the episodes. So each episode actually begins independently of how the previous episode has ended. So let's understand what are episodes and what are episodic tasks. So in simplest case, the interaction of the agent and the environment, it breaks naturally into chunks, which are called episodes, and each episode begins independently of how the previous one ended. And at the termination, the agent is reset to the start state, and every episode has a final state which we call the terminal state. So we call these kind of tasks as episodic tasks. So let's take an example of an agent who is trying to solve a maze. So a game of maze always ends with either an agent either solving the maze or hitting the wall. So a single game of maze would constitute an episode. So each game starts from the same start state with the position of the agent reset. And we can also take the example of a tic-tac-toe game where the agent is trying to win the game. So either each episode ends by winning the game or losing the game. So that is either the 3 X's will be in a sequence or 3 zeros will be in a sequence. And each episode ends by either winning the game or losing the game. So there are other types of problems with the agent environment interaction. It goes on and it continues without any end. And such type of tasks are called as continuing tasks. So continuing tasks, they cannot be broken up into independent episodes. So the interaction goes on continually and there are no terminal states also. So let's take the example of a robot who is trying to learn how to walk, and since the robot and the interaction or with the environment will never end, so the robot will go on interacting with the environment continually, and the reward for this robot would be negative every time the robot destabilizes. So every action that the robot takes, if it destabilizes the robot, will give a negative reward, and since the robot never stops interacting with the environment, so we have to give it a negative reward every time it destabilizes. So also to avoid negative reward, the robot would learn to avoid the actions that destabilize it. So this is one example of how continuing tasks will work. And we can also take the example of a smart thermostat which regulates the temperature of a room. So this can be also formulated as a continuing task, since the thermostat will never stop interacting with the environment, and the state of the thermostat could be the current temperature along with other details such as the time of the day and the number of people that are present in the building. So there are just 2 actions, either to turn on the heater or turn it off. So the reward would be negative every time someone has to manually adjust the temperature, and otherwise it will be 0 reward. So to avoid a negative reward, the thermostat will learn to anticipate the user's preferences according to the day of the time and the number of people that are present in the building. Now if you try to sum up all the future rewards as we have done in episodic tasks, so now there is one problem that we are summing over an infinite series. Since this series will never end, it will keep on continuing. So to solve this problem, we'll modify this sum so that it becomes a finite sum. So one solution is to discount future rewards by a factor. So here gamma, which is called the discount factor, so the value of the gamma, which is a parameter which is called the discount factor, it can be 0 or less than 1. So it can be either 0 and less than 1 or 1. So the effect of discounting on the return will be that the immediate rewards will contribute more to this sum, and rewards which are far into the future, they will contribute less because they are multiplied by the gamma which are raised by the powers successively. So the rewards which are in the future, they will have a less contribution compared to the rewards that are currently estimated. So we can choose to write this sum as this expression. So once we have this expression is now infinite. But if you want to make this finite, so we'll concisely write the sum as this expression, which is guaranteed to be finite. So this expression is guaranteed to be finite. So to get here from this expression, we'll assume that R max is a maximum reward and that our agent can receive. So we'll pull this term out of the equation since it will be a constant. So because this is the maximum reward that our agent can receive. So now the second factor here, which we are left with, it's just a geometric progression or geometric series. And the geometric series, it is always a finite series. So the R max times 1 divided by 1 minus gamma is a finite, and it is the upper bound on the GT. So the GT will have the R max multiplied by 1 divided by 1 minus gamma, which will be a finite series. So now if we look at the gamma value here, so if the gamma equals 0, so the return of this function will just be the reward at the next time step. And we say that in this case, the agent is short-sighted and only cares about the immediate reward, not the future rewards. On the other hand, if the gamma value is 1 or is closer to 1, it cannot be 1, it can be closer to 1. So if it approaches 1, the immediate reward and the future rewards both are counted nearly equally in this return. So in this case, we say that the agent is far-sighted. So now our agent actually counts both the immediate rewards and the future rewards. So that is why we say that the agent is far-sighted. So now let's discuss a simple and one more property, very important property for the returns. So which we call as the recursive nature of the returns. So the returns can be written recursively using this particular equation. So we have pulled out gamma from the terms starting from the second term in our sum, and the sequence in the parentheses here is actually the return on the next time step, that is t plus 1. So we can write this particular term as the return at time t plus 1, which would be gt plus 1. So now we have a recursive equation with gt on the left hand side and gt plus 1 on the right hand side. So later on, this term is actually the return at time t plus 1, which is equal to gt plus 1. So this is the equation that we get finally, where on the left hand side we have gt, which is the return at time t, and we have on the right hand side gt plus 1, which is the return at time t plus 1. So later on we'll use this equation to design our learning algorithms. So earlier we have discussed that the agent's role in an interaction is to choose an action on each time step. So the choice of the action has an immediate impact on both the immediate reward and the next state. So in this video we'll describe what are policies and how an agent selects these actions. So a policy maps each state to a single action, and we use the Greek letter pi to denote a policy, and pi of s represents the action selected in state s by the policy pi. So if the agent is following a policy pi at time t, then pi of a given s is a probability that action a is selected when the state is s. And a policy can only depend on the current state and not on any other factor like time or previous states. So the current state should have all the information that is used to select the current action. So a policy that maps each state to a single action is called a deterministic policy. So in this example that we'll see, policy pi selects action a1 in state s1 and s2, and it selects action a2 in state s3. So you can notice that the agent can select the same action in multiple states, and some actions might not be selected in any state. So in general, we can say that a policy actually assigns probabilities to each action in each state. So we use the notation pi of a given s to represent the probability of selecting action a in state s. A stochastic policy is the one where the multiple actions may be selected from a single state with non-zero probability. So here we have shown the probabilities over actions from state S1 according to the policy pi, and you have to remember that the pi specifies a separate policy of actions in each state. So for different states there will be different policies or policy distributions that are specified by the policy pi. So we can say that the sum over all the action probabilities must be 1 for each state, since it is a probability distribution. So the sum over all the action probabilities must be equal to 1, and each probability must be non-negative. So each action should have a probability that is non-negative. So in conclusion, an agent's behavior is specified by a policy that maps the state to a probability distribution of different actions, and a policy can only depend on the current state and not on any other factors such as time or previous states. So in reinforcement learning, a reward captures the short-term gain. However, our objective is to learn a policy that achieves the most reward in the long run. So we use value functions to formalize this notion. So we'll start by understanding what is a state value function. So a state value function is the future reward that an agent can expect starting from a particular state under a policy pi. So more precisely, the state value function is the expected return from a given state. So GT is our return, and we are in state S. So this is the expected return, and we denote our state value function using V of pi of S. So the agent's behavior will also determine how much reward it can expect in the long run. So a value function is defined with respect to a given policy. Here we have specified a policy pi, and where our return is gt, which is given by this expression that we have seen before. So we can also define an action value function. So an action value function describes what happens when the agent first selects a particular action and then follows a policy pi. So more precisely, the action value of a state is the expected return if the agent selects an action A and then follows a policy pi. So here our return is gt, and we are in a state S and we took an action A. So what is the expected return when an agent selects an action A and then follows a policy pi? So value functions are basically used to judge the quality of different policies, and a value function also allows an agent to determine the quality of its current situation instead of just waiting and looking to observe the long-term outcome. And value functions basically also summarize all the possible futures by averaging over the results. So in reinforcement learning, the agent's goal is to avoid negative rewards in the future by recognizing similar experiences in the past when it got a negative reward. So in reinforcement learning, a similar idea that allows us to relate the value of the current state to value of future states without actually waiting to observe all the future rewards, which is called the Bellman equations. So we use the Bellman equations to formalize the connection between the value of a state and its possible next states. And we also use Bellman equations to relate current and future values. So Bellman equations express a relationship between the value of a state and its possible next states, and also they can be used to express a relationship between the state action pairs and the next state action pairs. So the Bellman equation for a state value function defines the relationship between the value of a state and the value of its next possible states. So let's start by recalling that the state value function is defined as the expected return starting from the state S, and recall that the return is defined as the discounted sum of future rewards given here. And we have seen previously that the return at time t can be written recursively as an immediate reward plus and the discounted return as a return at time t plus 1. So the gt plus 1 is a discounted return at time t plus 1, and this is the immediate reward. So now let's expand this particular equation. So first we'll expand the expected return as a sum of all the possible action choices that are made by your agent, and second we expand over the probability distribution and over the possible rewards and the next states condition on state S and action A. This is our next state and this is the reward, possible rewards and next state on this current state and current action. So we can break it down in this order because the action choices depends only on the current state. So while the next state and the reward, they only depend on the current state and action. So this result is actually a weighted sum of terms consisting of immediate reward plus an expected future return from the state S prime. So here all we have done is just explicitly write the expectation as it is defined. So it is the sum of all the possible outcomes weighted by the probability that they occur. This is the sum of all the possible outcomes and this is weighted by the probability that they occur. And you can also notice that this t plus this rt plus 1 is a random variable, while this particular r, small r, represents each possible reward that we receive or reward outcome. And the expected return, it depends on states and rewards that are infinitely far into the future, which is represented by or gamma here, and this is expected return which depends on states and rewards infinitely far into the future. So we can also notice that this particular term here is the expected return, is the definition of the expected return for the value function for the state S prime. So for state S prime, this is the expected return and the definition of the value function. So the only difference here is that the time index is t plus 1 instead of t. So, and this is also not an issue because neither the policy nor the p, which is the probability distribution, they depend on time. So if we replace this one with v pi of S prime, which is the expected return for the state S prime, so we'll get this equation which is called the Bellman equation for the state value function. So we'll use this equation later on to find the value functions for different states and represent each state in relationship with the values of the future states. So we can also derive a similar equation for the action value function. So it will be a recursive equation for the value of the state action pair in terms of the next state action pairs. So in this case, when we expand the equation, you can see that the equation does not begin with the policy selecting an action as it was in our state action value function. And this is because the action is already fixed as a part of our state action pair. So again, we have a weighted sum of terms consisting of immediate reward, that is R, and plus the expected future return given by a specific next state, that is S prime. So unlike the Bellman equation for the state value function, we cannot just stop here because we want a recursive equation for the value of state action pairs in terms of the next state action pair. So at this moment, we just have the expected return given by one state, that is S prime. So we don't have any action included here. So now to change this, we can express the expected return from the next state as a sum of the agent's possible action choices. So in particular, we can change the expectation to be conditional conditioned on both the next state and the next action, which is given by S prime and A prime, and then sum over all the possible actions using the summation here. So here each term is weighted by the probability under pi of selecting the action A prime under the state S prime. So now if you look at this particular equation or this particular part here, you can see that this is the expected return is the definition of the value function for the S prime and A prime. So this expected return is just the definition for the action value function for S prime and A prime. So if we replace this, we'll get this equation here. So this is the Bellman equation that we'll use for the action value function, which where this is the same equation here that represents this part, which is the action value function for the state S prime and the action A prime. So this is the action value function or the Bellman equation for the action value functions. So later on we'll discuss why this relationship is so fundamental in reinforcement learning and how we can use it to design algorithms which can efficiently estimate the value of value functions. So now let's look at some examples of the Bellman equations to get some clarity. So we'll start with our first example. So let's say there are three states S1, S2 and S3, and the returns that are given by each state as minus 0.1, minus 0.1 and 1. So if you transition from state S1 to S1 with the probability of transitioning is 0.3 and the return that it will give you or the reward that it will give you is minus 0.1. And if you transition from state S1 to S2, probability of transitioning is 0.7 and the reward that you will get is minus 0.1. And if you are in state 2 and you transition to state 1, the probability of transitioning to state S1 is 0.6 and you will get a reward of minus 0.1. And if you are in S2 and you transition to state S3, which is the final state here, so the probability of doing that is 0.4 and the reward that you will get is plus 1. And from S3 you cannot go anywhere because that is the final state. So now let's write Bellman equation for the state value functions using this particular MDP. So let's assume that the value of gamma here is 0.9, which we will see later how to take the value of gamma. So we'll take the value of gamma as 0.9. So let's calculate the Bellman equation for each state. So we'll start with the first state, that is S1. So our V of S1 is this one. So here, since our action policy is only to transition from one state to another, so the first term in our Bellman equation, the probability of each action will be 1. That is why that term is not included. So if we have multiple actions with different probabilities, so we would have to take those probabilities in account as well. So here our probability is 1 for each action. That is why the first term will be 1. So we'll focus on the next term, that is probability of selecting S1 when we are already in S1. So if you look at this particular action here, so the action was to transition from state S1 to S1. So we'll calculate the state value function for the S1. So our first term here is this one. So here P of S1 given we are in S1, which is the probability of selecting S1 when we are in S1 state. So it is 0.3 and then the reward that we'll get is minus 0.1 and the value of gamma that we have chosen is 0.9 and then V of S1 is what we are calculating here. So we'll get an equation of this form, and the second term, the second transition that we can do from state S1 is to S2, which has a probability of 0.7 and then reward that we'll get is minus 0.1 and then the value of gamma is 0.9 and then we have the value of state S2 that we'll calculate later on. So the final equation that we'll get is this equation. This is our state value function using the Bellman equation for the state S1. So now let's calculate the same for the S2. So if we calculate the same state value function using the Bellman equation for S2 state, you will get this equation where this term will be the transition to state S1 and this term will be the transition to state S3. And if you calculate the state value function for the state S3, it will be 0 because we are not transitioning to any other state from S3. So now we have three equations and this is called a system of linear equations. So we have three equations and three unknowns, that is V of S1, V of S2 and V of S3. So you can use online calculator, or if you know how to solve system of linear equations, you can solve it, and after solving you will get this particular values. So for each state we have a state value function or the state value. So the value is 0.293 and 0.498 and the value for the state S3 is 0. So this is how we use Bellman equations to calculate the state value functions for our different states in an MDP. So let's discuss another example which is called the grid world. So in grid world, our different states are represented by rectangular boxes. So suppose that we have four states called S1, S2, S3 and S4, and our policy that our agent is can select is either the agent can go upwards, rightwards, downwards, or leftwards. So there are 4 actions that our agent can choose in each particular state. And suppose if you are in state S1 and if you choose the action right, so you will transition to state S2, so you'll get a reward of 0. And if you are in S3 and if you choose the upward action, the agent selects the upward action, so it will transition to the state S1, so it will get a reward of 0. And the same happens when you transition from S2 to S1 to S3. So the only time that we get a reward is when we transition from any state to S4. So if you are in S3 and you choose the rightward action and you transition to S4, so you'll get a reward of plus 10. And if you are in S2, if you transition to S4 using the downward actions, then also you'll get a reward of plus 10. And suppose if you are in S4 and you press the right button or the rightwards action, so you will bounce back into the same state, that is S4, and then also you'll get a reward of plus 10. And if you are in S4 and you press the downward action, you'll bounce back to the same state, that is S4, so you'll get a reward of plus 10. And this happens in every single state. So if you are in S2 and you press the right button or the rightwards action and the agent selects the right action, so it will bounce back to the state S2 with a reward of 0. And the same will happen in every single state. So now let's assume the value of gamma equals 0.7. So we'll take the value of gamma is 0.7 and we'll calculate the value function, the state value function for each state using the Bellman equation. So this is our Bellman equation. So here if we simplify this, so this part will be 1 because the probability of transitioning from any state to any other state is 1. So we'll take this probability as 1, but our action probability will be different. So here, or if you are in state S3, let's calculate the value function for the state S3 first. So if you are in state S3, so based on the actions that you take in S3, we'll sum up all the values. So here R is the return that you will get after transitioning and gamma value is 0.7. So this is the value of S3 that we'll get. So the first transition can be if the agent selects the right action, so it will transition from the state S3 to S4. The reward will be plus 10 because we are transitioning to S4, and then the next value is the gamma value is 0.7, and then the value of the state S4 that we don't know yet, and then plus the next transition can be from S3 to S1, so it will be 1 by 4 since the probability of selecting each action is 1 by 4. So we'll get 0.7 because the return value is 0, and the next expected value for the next state is value for state S1 that we don't know yet. So third term that we have added is when we choose action. So if you choose the right action, you will get this probability, this term here, and if you choose the upward action, you will get this term. And if you choose to go down or go leftwards in S3, so that will be counted as 2 actions. So when you combine that, you will get this 1 by 2, 0.7 into value of S3 because you will bounce back to the same state, that is S3. So this is the equation for the state value function using the Bellman equation for state S3. So now let's calculate it for all the states. So these are the 4 equations that you will get when you calculate the state value functions for all of these states. So once you have these 4 equations, you have a system of linear equations. You have 4 variables and 4 unknowns, 4 equations and 4 unknowns, and you can solve it using matrices, or you can use online calculators also to solve this system of linear equations. And after you solve these equations, you'll get the value for each state. So the state value for the state S3 is 7.98, for state S1 is 3.38, and for state S2 is 7.98, and for state S4 is 11.99. So the highest state value is 11.99. So if you are in S2 and if you want, for agent wants to know which state is best, so it will look at the state values. The state values for the S4 state is the highest, that is 11.99. So we can directly transition to the state that has the highest state value, and the same will happen if our agent is in state S3 and if it wants to know which action is the best or which state is the best. So you can look at the state values for each state and then we can transition to that particular state. So for small MTPs where we have small number of states and probabilities, so we can use system of linear equations to find the value functions using the Bellman equations. But for larger problems where we have thousands of states, it is not feasible to use system of linear equations. So later on in this course, we'll use other methods using the Bellman equations for MTPs that have lot or a huge number of states. So till now we have seen that a policy specifies how an agent behaves, and given this way of behaving, we then aim to find the value function. So our ultimate goal is to find a policy that obtains as much reward as possible in the long run. So in this video, we'll achieve this notion with the help of the optimal policies and optimal value functions. So an optimal policy, which is denoted by pi star, is a policy which is as good as or better than all other policies. So we say that a policy pi 1 is as good as or better than the policy pi 2 if and only if the value under pi 1 is greater than or equal to the value under pi 2 for each and every single state. So which means that an optimal policy will have the highest possible value in every state, and there is always at least one optimal policy, but there may be more than one as well. So now the value function for an optimal policy has the greatest value possible in each and every single state. So we can express that mathematically by writing that pi star of s is equal to the maximum value over all the policies. So this will hold for every single state in our state space, and the value for an optimal policy is defined to be the largest of all the computed values, and we could repeat this for every single state, and the value for an optimal policy would always be the largest. So all optimal policies have the same optimal state value function, which is denoted by v star here. So optimal policies also share the same action value function, which is again the maximum for every state action pair. So we denote this shared action value function by q star here. So right now let's move on, and we can rewrite the Bellman equations for the state value functions in a special form. So in this form, we don't actually reference the policy itself. So there always exists an optimal deterministic policy that will help us select an optimal action in every single state. So such a deterministic optimal policy will assign probability 1 for an action that achieves the highest value, and for all other actions it will assign a probability of 0. So that is how we can express this another way, by replacing the sum over pi star here with the maximum over a. So we have derived a relationship that applies directly to v star itself here. So we call this special form the Bellman optimality equation for v star. So we can make the same replacement in the Bellman equation for action value function, so which will give us the Bellman optimality equation for q star. So earlier we have discussed how the Bellman equations form a linear system of equations that can be solved by standard methods. So optimality equations also give us a similar system of equations, but now the system will not be a linear system of equations, since we are taking the maximum over actions, and the maximum over actions will not return as a linear system. So later on in this course, we'll use different methods to solve these equations, and we'll also see how the correspondence between the optimal value functions and optimal policies will help us derive reinforcement learning algorithms. Just a quick info, guys. If you want to become a certified professional in reinforcement learning, Intellipaat provides a complete course on reinforcement training and certification. For further details, you can check out the description box below. So this brings us to the end of this session. If you have any queries, you can write them in the comments section below, and we'll reach out to you as soon as possible. Thank you for watching this video, and happy learning.